My name is Rafael Mayo. I'm from University Jaume University of Castellón, and here is Tony that will speak later. We are going to introduce rCUDA 4, that is the work we are doing as a research effort, a joint research effort between Technical University of Valencia and Universitat Jaume University. Here's the line of the presentation. First, I will give.
Just a little higher.
Okay. Here?
Yeah.
I will give a small introduction to GPU computing. The GPU computing scenarios we consider for our tool, our wish list, and the introduction to rCUDA. Finally, the last 4 points will be done by Tony, in which he will introduce the internals of the tool. Well, as all you know, GPU computing defines all the technological issues for using GPUs as a general purpose computation, and has experienced a big growth in the last years. Here you can see a typical plot of the top 500 supercomputing using GPUs from the June 10th, 2010 to June 2012. You can see before this list there is no supercomputing using GPU computing, and now it's growing almost exponentially the use of GPU computing in the high performance computing. Then the basic building block for a GPU computing is a cluster in which in a node we introduce GPUs to use as general purpose accelerators. These GPUs can be inside the CPU box or outside the GPU box. But in both cases, GPUs are connected to the CPU system via the PCI Express bus. As you can see, you can have between 1 and last system has up to 8 GPUs in one node. Then, from the programming point of view, the system can be seen as a cluster. It's clustered with one or more CPUs, with several cores per CPU, and one or more GPUs up to. I think the number must be 8. There's some system with 8 GPUs, no? And an interconnection network. The most important thing from the programming point of view is that GPUs and CPUs don't share the memories. That is, GPU has his own memory space, and CPUs has its own memory space, and must be connected via the interconnection bus. This is the PCI Express. Normally, interconnection network, as Professor Peña has said, is InfiniBand for high-performance clusters. For the development point of view, there are two main approaches, CUDA and OpenCL. You know, the two main approaches has been done in order to ease the programming of GPUs, and basically both approaches has the same working scheme. That is, in the compilation step, we generate CPU code and GPU code. The GPU code is the GPU kernel. And in the execution step, there must be data transfer between GPU and CPU memory spaces. That is, before the GPU kernel execution, we have to move data from the CPU memory space to the GPU memory space. Then we can execute the kernel in the GPU, and after the execution, we have to move the results from the GPU memory space to the CPU memory space. That is an overhead in the execution of kernels in the GPU. Here in this plot, you can see the ratio between the data transference and execution in the GPU. This is for a matrix multiplication, and as you can see, as we have more work to do in the GPU kernel, the ratio is better in order to obtain benefits from sending data to the GPU kernel, executing there, and taking back the results to the CPU memory space. Then we consider for the right kind of code that, for us, the right kind of code has two main aspects. The first one is the ratio between transfers and GPU execution, and the second one is the data parallels that must be in the code that will be executed in the GPU. That if no data parallel appears in this code, you cannot take benefit of executing in the GPU. So we consider 4 different scenarios. Scenarios with low-level data parallels, with high-level data parallels, with moderate-level data parallels, and applications for multi-GPUs. For the two first scenarios, that is the low-level data parallels, what happens regarding the GPU computing? We consider that in this case, the use of GPU computing is not good. We don't need to use a GPU if we don't have a code with data parallels. For the high-level data parallels, that is, we have code that has a good ratio between data transfers and GPU execution, and in the GPU kernel you have a lot of data parallels. Just we think that the only to do is to add all the GPUs you can do in each node and use these GPUs. And in these two scenarios, the tool that we are going to present is not useful. First one, because no GPU is needed, and the second one, because the actual organization, the actual architecture of the supercomputer using GPU computing is good enough. Then, what happens with moderate level of data parallels? That is, applications that you can use GPU for between 40 and 80%, more or less. What happens in this case? In this case, if you put GPUs in all the nodes in the system, you can use only these GPUs for a reduced part of your application. In fact, for 40 to 80% of the time. That is, the rest of the time, the GPUs will be idle, and you are going to have a waste of resources and energy. And the fourth scenario, the applications for multi-GPU computing, in the nowadays clusters of high-performance computing using GPUs, the application running in one node are limited to use the GPUs in this node. So you have an application in one node that can be used more than the GPUs that are connected in this node. They are limited to the GPUs in the node. You have only 2 GPUs per node. You can only, in an application, these GPUs per node. Although your application can use more GPUs if they will be accessible. Then, once I introduce our idea of GPU computing, I think you know all of I say until now. I will introduce our wish list. What is what we want to do with our project? The current trend in GPU deployment is something similar like this. You have a cluster, and each node in the cluster has the GPU computing and the CPU part. Then, as I said, for moderate level of data parallels, you will have GPUs either for long periods of time. And for multi-GPU applications, from each CPU, you can only access to the GPU that is connected in that node. Then, with a cluster of this type, you have a high deployment and energy cost, because you have to buy GPUs for all the nodes, and you have to use energy enough in order to supply power to all the GPUs in the cluster. How we can reduce this? In order to reduce this, the first approach is Don't put GPUs in all the nodes. Put only GPUs in some nodes in the cluster. But what happens if you make a cluster of this architecture? Then the problem is that when an application are going to use a GPU, you have to schedule the application only to the node that has GPU directly connected. Then this will increase the difficulty of scheduling jobs, and may have nodes with a lot of load, because all the applications with part of the GPU work are putting in this node, and will be nodes with a low load. Our thing is that what we want to do is reducing the number of GPUs, but put some tool that may share these GPUs with all the nodes in the clusters. That is, we can access this GPU from all the nodes in the clusters, or whatever GPUs in the clusters can be accessed from whatever node in the clusters. So we can share the GPUs with all the GPUs, and we can reduce the two parameters of the cost, the initial cost of the clusters, and the energy cost of maintaining these clusters. Then we introduce our tool, rCUDA, that try to efficiently sharing the GPUs across the cluster. As far as we know, there is other tools that try to do the same, but our tool is the only one that supports CUDA 4 at the moment. This is our other projects that are trying to do similar things that we are doing with rCUDA. Going beyond, our view is that in a future we can have GPU modules like we have now storage modules that will bring power to whatever CPU in the system. That is, we can have a box of GPUs and share these GPUs with all the CPUs in the system. Then we disaggregate. We try to disaggregate GPUs from CPUs, and we have to obtain some type of scheduler that for each application schedules the beta GPUs in the cluster that are available intermodal. Then, what is rCUDA then? rCUDA is a middleware, a framework that enables a CUDA-based application running in one node to access GPUs in other nodes. We consider this framework useful when we have a moderate level of data parallelism or application for multi-GPU computing. What happens in moderate level of data parallelism? In that case, this is the typical architecture of a GPU computing cluster. Then, as I say, adding a set of GPUs to all the nodes is a waste of money and energy. We instead propose to add GPUs only to some nodes in the cluster. That is, you have considering the application requirements and the level of data parallelism in this application, and you add the GPUs that you will need in this cluster, and put a middleware in that with logical interconnections make this GPU accessible from every node in the cluster. In the second scenario, when we have application for multi-GPU computing, in a typical GPU computing cluster, the application running in this GPU can only access to the GPUs in this node. That is, in this case, each application will be limited to 2 GPUs for the use of the application. Instead of this, as in the previous one, we propose to put all these GPUs in a pool and with logical interconnection, make it possible that an application running in one CPU can use as many as GPUs they need at this, in each moment. So an application running in this GPU is not limited to the 2 GPUs directly connected in the node, but can use all the GPUs in the cluster. Then, once I introduce rCUDA, Antonio will give you more details about the internals of this tool.
Okay. This is how typical CUDA applications work. With original CUDA, an application accesses the real GPU device through the CUDA libraries. But in our environment, we have the application in a different node, in a separate node, than the real CUDA device and the CUDA libraries. So we have to place some middleware, some way to enable that application to access the real CUDA device and the CUDA libraries on the server node. So this is how we do it. We place on the client side and a library replacing the original NVIDIA CUDA runtime library, and on the server side we add the rCUDA service, the rCUDA server. It's the rCUDA daemon. Those middleware actors communicate themselves through the network interconnect. The rCUDA library is a replacement of the NVIDIA one, and it exposes exactly the same API. So applications are not aware that they are dealing with the rCUDA library instead of the original CUDA one. And this library is in charge of intercepting the calls to the CUDA runtime and forwarding them to the server side where the rCUDA daemon is listening for requests. And this daemon is in charge of executing the remote requests in the real device and send back the result of those executions. Well, our communication protocol between clients and servers is designed in a way that it involves as little computations as possible. So in the most common case, for each intercepted CUDA call, the client sends a message to the server, including a function identifier and the parameters of that function call, and the server sends back the CUDA result code and more data depending on the particular function code, such as for instance the CUDA malloc, it returns the result code followed by the device pointer of a new allocated buffer. Another important thing here is that we don't extend the original API with initialization or termination functions. They are done automatically by the middleware. Well, we have our latest stable release is rCUDA 3, and it uses the TCP/IP stack, and hence it runs over a wide range of environments, such as Ethernet or even InfiniBand networks. And also, it's also usable in virtual machines in order to expose the GPGPU capabilities of the real hardware to the virtual machine through the virtual network connection. As TCP is not designed for HPC for the HPC arena, it presents some overhead in some cases which is not negligible, and this is addressed in the new rCUDA 4 release. Here we have some numbers for performance for the rCUDA 3 release. This is a matrix product done in the CPU employing 8 cores, and also in a remote GPU going through a gigabit Ethernet interconnect with rCUDA. We can see how for large enough problems, doing that doing the matrix product in the remote GPU is faster than employing the local CPU. So if we don't have a local GPU, we can use a remote GPU and go faster than if employing the local CPU. We can see here that a large amount of time is devoted to transfers. So transfers across the network. So if we can reduce these data transfers, we will get very fast remote accelerations. So this is done employing high-performance interconnects and also employing them efficiently. Well, our new release is rCUDA 4 is still on an alpha release. The first capability it includes is low-level InfiniBand support, because InfiniBand is the most used HPC network currently, as we can see in this plot extracted from data from the last top 500 list. And with InfiniBand, we can reach high bandwidth and low latency. From the user level point of view, the new rCUDA 4 exposes the same functionality as it exposes the CUDA runtime. Now we are supporting 4.2, but rCUDA for CUDA 5 is coming. Well, in this release, we included a communications module making use of low-level InfiniBand bursts to efficiently make use of the InfiniBand interconnects, so that we can avoid the overhead introduced by TCP/IP. This way, we can attain a very high use of the InfiniBand interconnect. So we also use the first generation of GPU Direct to avoid intermediate memory copies, and we also perform network and GPU pipeline transfers to attain a high level of efficiency. Once the GPU Direct RDMA support is available, we will also introduce the transfers making use of this new capability. This is how we currently perform transfers in rCUDA 4. From a client side to the GPU memory of the server side. We do it in a pipeline fashion. So the first stage of the pipeline transfers the data from the main memory of the client to the main memory of the server, and the second stage concurrently transfers the data from that memory, the main memory of the server, to the GPU memory. This is employing the first generation of GPU Direct. When the next generation, the third generation of GPU Direct is available, GPU Direct RDMA will be able to avoid the intermediate copy to the intermediate transfer to the main memory of the server, and we will avoid using that memory and getting a lower latency. And hence the memory is not stressed by the rCUDA service. Here we have some numbers for transfer performance using rCUDA 4. In this system, we reached with a new InfiniBand burst module 97% efficiency of the network interconnect to transfer data from the client to the remote GPU. And if doing it through the TCP/IP stack, we had probably half performance. So that's why it's important having the InfiniBand-based communications module. Of course, we are very far from gigabit Ethernet performance, and we have here that native CUDA is performing faster because it doesn't go through the network interconnect, but this is QDR, and we don't have numbers yet for FDR and the new generation of Kepler GPUs, but this is going to improve even more. Here we have, again, numbers for performance of matrix-matrix product. We can see how the overhead introduced by rCUDA through the Infinima interconnect, this is also QDR, is almost negligible, and remotely accelerated matrix-matrix product is much faster than the locally executed one in the CPU. Here we have the global, the overhead introduced in the global execution, in the total execution, by the data transfers to the GPU. We can see that, of course, with rCUDA we have a little more overhead because of we have the GPU far. We have to traverse the network, but for, the difference of the overhead is almost negligible for large enough problems. And here we have a far more complex execution. This is the LAM simulator, and we can see that in this case, if employing regular CUDA, we can save 24% time. But if employing rCUDA, a remote GPU with rCUDA, we only have 3% difference. So we can save over 20% time if employing a remote GPU with the advantages of having the global shared pool of accelerators. But there's more than Infinima support and pipeline transfers in rCUDA 4. We also made the client-side thread safe. Now multi-threaded applications can access GPUs in a remote node. We also added multi-server capabilities in order to one application is available now to access the GPUs placed in different GPGPU servers. And even more, we can combine both capabilities in order to have multi-threaded applications accessing the GPUs placed in different nodes. What we don't have yet implemented in this alpha release is GPU Direct 2 emulation, so that if the application tries to perform a device-to-device memory transfer between GPUs placed in different nodes, it's not working yet. We have to implement direct transfers between GPGPU servers without further involving the application. Remember that the application is not aware that it's using remote GPUs and they may be placed in different nodes. Well, we have here some performance numbers for the new capability of multi-thread and multi-server. Here we execute a different number of matrix products, each one targeting, each one accessing a single GPU, a different GPU. In the case of CUDA, as Rafael said, we can have up to 1, 2, most computing nodes have 1 or 2 GPUs. Here we performed up to 4. We used a computing node having 4 GPUs. But with rCUDA, apart from having roughly the same performance, we can access even more GPUs. We can access potentially all the GPUs placed in the complete cluster. And the trend is maintained. Well, rCUDA per se doesn't support the C extensions of CUDA. The C extension, the most common example of the new syntax, the C extensions of CUDA, is the kernel call employing the triple chevron syntax. We don't support those extensions because they are supported by the original CUDA with internal functions which are undocumented. So in order to these constructs to work in rCUDA, we had to manually translate this into the plain C API in order to compile it with regular C compilers such as the GCC. Now we provide a tool to do this automatically. It's called the Q2RQ. We have developed it inside our development team. So with this tool, we can automatically convert the extended code to an extended code in order to use the plain C API. And with MVCC, we generate the device code to be executed by the GPU. And with this tool, we produce the host code, which can be compiled with a regular C compiler. This tool uses the CLang framework, such as the new MVCC, and in fact, it's a plugin for CLang. Okay. Here we have numbers for the conversion and compilation steps versus the original compilation. The times are pretty similar, even though for here the upper one plot is for the SDK examples from CUDA, and here the bottom plot is for the user CUDA package of lamps, which has over 14,000 lines of code. So our conversion and compilation steps are pretty similar to the original compilation in terms of compilation time. Well, what's the current status of our development? How compatible is our CUDA with CUDA? We support the whole runtime API, excluding graphics interoperability. I mean, such functions related to Direct3D, and OpenGL interoperability. So every other function of the runtime API is supported, including asynchronous transfers, support for textures, or CUDA streams. Every single operation, apart from those related with the graphics interoperability. So the SDK samples can be executed apart from those employing graphics or the driver API. Well, our current stable release is CUDA 3.2. As you remember, it doesn't do pipeline transfers. It uses the TCP/IP stack. It supports CUDA 4.2, excluding the graphics interoperability. It's not thread safe, and it only allows a single rCUDA server per application. Only a GPU module per application is allowed, which means that you have to place all device functions in a single source code file in order to compile it with MVCC and generate a single GPU module. CUDA-C extensions were unsupported, and we have an experimental build for Microsoft Windows. The new rCUDA 4, we have already released an alpha version, supports the same API. It includes TCP and InfiniBand communications modules. It performs GPU and network pipeline transfers, employing the first generation of GPU Direct. It includes multi-thread and multi-server capabilities. It also supports the C extensions by means of the Q2RQ tool. It now allows multiple GPU modules, and it has some kind of MPI integration, as it automatically spreads the tasks of the different tasks of MPI across the different GPUs. This is our to-do list. We are developing support for CUDA 5. We have the Internode GPU Direct 2 emulation to transfer data between rCUDA servers placed in different nodes. We have to implement we have to perform transfers with the new GPU Direct RDMA coming with CUDA 5, and we also have in mind to integrate rCUDA into SLARM in order that the global job scheduler to be aware of the new concept of a shared pool of accelerators, in order to be SLARM who assigns the different GPUs to the nodes, to the jobs. We also have to provide full runtime support. I mean, the graphics interoperability is still missing, and we are porting rCUDA 4 for Windows, and we have some other features in mind. We are discussing them. This is our website, rCUDA.net. You can order there a free binary copy of rCUDA. We distribute rCUDA in binary, but it's free for institutional use. We currently distribute rCUDA 3.2, the latest stable release, and also the alpha release of rCUDA 4. We support most of the Linux distributions supported by CUDA, and also our experimental build for Microsoft Windows. And well, this is the credits and our development team. And that's my last slide. Thank you.